Thank you, Vasily, and everybody in the department for inviting me to the first lecture of the semester. It's a pleasure to come and see old friends from the times I spent up north, 81, in that university that Jefferson established, and make new friends in this visit in 2017. I'm glad Vasilis joined this department that I see moving forward, exciting times even lying ahead of it. Today, I picked up a topic that is based on the most recent PhD student, Brian Bangana, and that is related to inference and learning over large-scale social networks. By all means, feel free to interrupt me during the presentation if I can clarify things. Maybe there are more equations than necessary. I would like to make sense with some examples. And as a motivating slide, let me open up by saying that this field that is referred to these days as network science is born out of the recognition that in some sense there are networks almost everywhere around us. And by that I mean things that are familiar to most of us through the Facebook and other social media, the internet, which is a natural large-scale network, but also something that is near and dear to Vasilis' research, the energy and power, where this department gets an excellent reputation on. And furthermore, to financial networks formed by different markets. And more recently, a topic that I enjoy working on brain networks, as well as gene regulatory and protein and interaction networks. So I want us to think of the tools that I will try to touch upon in the next 45 or so minutes in this general context of networks and network science, I should say. And the question is, what is the what are the challenges and opportunities to what this common denominator that is referred to as network science faces these days? So, first of all, at the network level, the challenges include the fact that the scale is huge. So we're talking about a number of data points that sometimes they even change dynamically, and they bring to us streaming data which are basically in the order of 6,000 tweets, for example, per second, if you are those of the current president. And oftentimes, the networks that create such huge data, massive data, come from unobservable topologies. You don't know who is connected with who exactly, and you may have an interest to this end. And these are major challenges, finding the underlying network. And what is desired for that is to come up with parsimonious network models, as well as develop efficient schemes that can draw inferences over network data. So the framework that I'm going to choose, and that this line of work from my students lies on, at the crossroads of statistical signal processing, or machine learning, optimization, and network. That's where the theme falls and the tools come from. And I will start with a collection of areas we have worked on. I picked up an example from each. The first one relates to visualization and dimensionality reduction to cope with the large scale of the social networks. And even if I tell you, reflect on the idea that I tell you, try to create a plot that will depict all the nodes in the internet. How would that look like, right? So even visualizing networks millions of nodes is a non-trivial task. And I want to tell you that there can be some rigorous mathematics formulated to address these problems. The next thing I want to touch upon pertains to network health monitoring and learning over large-scale networks. Then I will talk about how we can track the topology of an observed topology of networks by using information cascades, or Twitter messages, or the time that they have been broadcasted. And I will talk about time-varying networks in that sense. And if time allows, I will discuss how one can identify communities or groups of large-scale social networks. And I will conclude with some summary directions. So let's talk a little bit about visualization of social networks. So the goal here is to visualize networks with an emphasis on their hierarchical structure. So the typical way of doing that is to look at a graph that is being formed by a set U that includes all the nodes and the set epsilon that includes all the edges. And I will denote the cardinality of the network with this absolute value of the set of nodes, which is n. So I want to find a low-dimensional representation per node, which is described by a vector xi, one per node for the node I in this particular case. And this vector has dimensionality 2 or 3, so that you can put it in 2-dimensional space or 3-dimensional space and be able to visualize it. And you can capture the inherent structure of the network. Now, how do you approach such a problem? The one abstraction would be to say that I have in each node a vector y sub I, which is of huge dimension, and I want from the huge dimension of y sub I to go to 2 or 3 dimensions, to the p-dimensional, which is small, and then be able to graph it or visualize it. So suppose you are given nodal vectors yi, and there is a tool that's called linear embedding that helps you to reduce the dimensionality by formulating this 2-step problem. So in the first step, you are trying to find these weights, wij, that after being linearly combining these neighbors of a vector yi, you can come as close as possible to yi. So that means that locally at least, you can approximate nodes that can live over a manifold, which looks like this Swiss roll. You can locally approximate it with a plane. So if a node I belongs on a plane, locally it will be expressible by nearby neighbors which are on the same plane. So every Swiss roll can be approximated by a bunch of planes. So these wij's, if you solve it with appropriate constraint, then you can specify the graph or the weights. And then, this is of size q, which is greater than p. You could go down and then say, I have this connectivity that is described by wij. How can I embed vectors, which means points, that I can use to visualize my network, xi's, that obey the same geometry but have lower dimension? And that's the problem that is typically solved in local linear embedding problems. However, there are 2 challenges here. Question is, how do I identify these yi vectors per node? These are typically not available. However, there is this theory of kernels that can allow you to capture the relationships between the nodes without having available vectors per node. So this is what we are going to do in the first step. So we're going to use one-hop neighbors, and these kernels that will be
forming a matrix capital K will be the product of the so-called adjacency matrices of the graph. This matrix A is a binary entry. It has binary entries 0 or 1, where 1 signifies that the entry at point ij signifies that the node I and the node j are connected, and 0 that is not connected. So now imagine that you multiply this adjacency matrix A with its transpose, all right? Soon you will realize that this 0, 1 row of the matrix A will be multiplied by the jth column of the A transpose, which is basically the jth row of A, and it will have non-zero entries only when both the row I and the row j have ones, right? And if you sum all these ones, it doesn't take you too long to realize that the Kij will be a number that reflects the common neighbors of nodes I and j. Let's take a real life example. If we have a friend I and a friend j, these are two nodes, and they have very common friends, it's very likely they'll be looking alike as people, right? So the degree of common networks that can be brought up through the topology of the graph, right, the common friends, the common neighbors, provides a means of establishing relationships between nodes. And sure enough, so we don't need to know the yi, that's what I'm trying to convey. So long as you have a way of finding out the relationships, the nodal vectors are not necessary. So what do you do in this case? The previous least squares cost that I wrote can be expressed through this quadratic form, W transpose Ki W, where the Ki basically is built from the neighbors of the node I, this kernel matrix. And the vector Ki is formed by the knowledge of the common neighbors of the I with its neighbors. Okay. Nevertheless, I'm trying to say that per node I, it is possible to solve an easy problem. That one can be solved in closed form, right? And find the W that relates to node I. That we can do it for every node I. And it's not a difficult problem in size to solve. So it's tractable. And it only depends on the topology and the degree, the local topology and degree. So then we said that it may be massive. So in our second step, we can respect the hierarchy and also come up with a scalable algorithm to solve, now that we have the Wij's, we can go and solve the problem where we're trying to find two or three-dimensional vectors to represent. We're going to do the dimensionality reduction now. And if we notice, by employing a tool from optimization that is known as block coordinate descent, although the problem is non-convex, it is possible to solve it efficiently, even because the constraint that enforces the hierarchical structure decouples in every node. So let's see what is this constraint. This constraint tells you that the magnitude of this vector that I want you to plot in your visualization should be a monotonic function of the centrality of the node. So basically, the high centrality nodes should be closer to the center if this is monotonically increasing, or to the edges, to the periphery of the vector if it's monotonically decreasing. All right? So here is the problem that you can solve with modern tools. And let's see how things work in real life. So I looked at the Gnutella network. It's a file sharing network in two snapshots on August 4 and August 24. These have 11,000 nodes and 40,000 edges. And we use the node degree as the centrality measure. And this is where the constraint came into picture. And this is what you depict in a network of 40,000 nodes, edges, and 11,000 nodes almost. So in the first day, the picture looks like this out of this mathematical solution. And in the second day, it looks like this. So here, what you observe by this is that in the 3 or 2 weeks, I guess, till 20 days later, we see that there are more nodes that have smaller average degree. So by looking at the picture, you can get a sense of a hierarchical sense how things change in a network from one day to another. So the message of this visualization thing is to tell you that even though you may think that visualization of complex networks is something that touches upon the artists, I can assure you that engineers have a lot to say of how you can visualize networks to make sense out of hierarchies in the network. So the next topic I want to touch upon pertains to identification of anomalous behavior in a network. And for us to be motivated, we can draw an example from from the times we live. And there are a number of areas where you would like to identify strange users with atypical behavior. And the examples, are many. You are interested about email spammers, cyber criminals, and even terrorist cells that by being able to track this about this Abdelhaim, who was suspected or is organized and arguably of the Paris attacks, the question that we want to pose is, by looking at his emails that he exchanged with accomplices, is it possible to come up with an early detection of anomalies that can halt future terrorist attacks? So it can be something of interest, certainly for national security. And what is we're going to use the egonets. And the egonets, I will demonstrate the notion in the next slide, are those that look at a network, and for every node, they construct a subnetwork that looks only at the first hop connections and the connections of the first hops. So ego comes from selfish, right? Self network for each node. So why did we use these features why did we select these features? Because there's an obvious challenge. There are far too many users, billions of people all over the world, if you're talking about cells. But every user has a few distinct features. And we're going to leverage that. So we're going to adopt the egonet features and leverage the structure of the network that is described by modern attributes such as sparsity and low rank to identify anomalies. So this gentleman carried out, this paper by Koglu, carried out simulations to demonstrate that egonets, which are the ones that I'm showing there, as I said, for each node, in here the red node, I'm looking at one-hop connections and the connections of the one-hop connection. So this is the egonet of each node. So this gentleman, with simulations, motivated us to look at a rigorous formulation of the problem. And here is what we came up with. So we looked at an n-node graph that has features y1 through yn. These are columns of a vector of size d by n. D is the dimension, n is the number of vectors we have. And for each node, we collected d features. And these are the degree of the node, the centrality. These are different nodes. How important is a node? How many paths go through this node? These are questions that characterize the node itself. And then we used another result from computer science that people recognized that nominal features, such as the degree, when viewed as random variables, they are drawn from a distribution with heavy tail. So that means, this is a power law that people refer to. So that means even the probability of having a small number of connections is high. And that motivates us to say that fundamentally this y comes from another matrix X that has low rank. So the power law, we translate it into low rank. Okay? And whatever strange thing happens, we collect it in an outlier or O matrix for anomalies, plus noise to model and modern dynamics. So the problem is, if one is given X, can you identify the X and the O? That sounds too challenging, right? Just to tell you that it's a fundamental problem, reflect on the fact that 25, which is the y, and entry in y, can be 21 plus 4, can be 20 plus 5, can be 28 minus 3. So all I'm saying is, can you, from the sum, identify the summands? That's a tall proposition, right? Is it impossible? Well, but I told you two things. Actually, I told you one, and I forgot to say the second one. The first one I told you is that this is a low-rank matrix. Automatically, what I told you is that not all the columns are linearly independent, right? So the real unknowns are less than what it looks. And I also forgot to mention that this outlier matrix or anomaly matrix is sparse. Why? Well, because if it was not sparse, it would not be called outlier, right? It would be nominal or inlier, if you like. So, leveraging these two properties, we're going to proceed. And also, I forgot to say, because I already mentioned that these matrices could have massive dimension, billion people, right? But still, we're hopeful, even if we use a projection operator to extract only the observable entries, still it may be possible to unveil X and O. So basically, it's like a puzzle, right? This is like a puzzle. So then you pick up some of the pieces, then you may be able to figure out who is missing and know how to impute the pieces, and then figure out the anomalies. Just to have a concrete example in our brains, in our minds, you know, for the terrorist cell, right? If all of a sudden I start counting the number of phone calls between these guys, and on a certain day before the attack, these phone calls, number of exchange of emails spikes. That's what I want to see, and since I monitor them, I can track them closer, right? So again, we formulated, I skipped the mathematical details, but I think that should be enough. So we formulated an optimization problem that entails a least squares cost that tells you how close this model y minus x minus o is to the noise level. And then we utilize two constraints to affect the attributes that I mentioned. And the first constraint is the nuclear norm to affect the low rank of matrix A. And the second one is the L1 norm that in recent years you may have heard is sparsity efforts and lasso, so-called lasso approaches, whereby the L1 norm is a convex surrogate of the zero norm that basically counts the number of non-zero or zero entries or non-zero entries correspondingly of the matrix O. So by tuning these lambdas, you can tune the sparsity and the rank of the summands X and O. So as I said, the L1 norm is the sum of the absolute values, and the nuclear norm of X is the sum of the singular values, which clearly reflects the rank of the matrix X. So let me just give you an example. This is the archive collaboration network. So there is a journal called General Relativity, and every node is an author that has submitted over 10 years a paper in this journal. Okay? And if there are two people who have collaborated or I don't remember if it's collaboration or citing each other, one of the two, but they are somehow related, then we draw a link. And then you would come up with outliers that in this case, they're not necessarily the bad guys, but the guys that provide more information and they are very well connected with other people. So these nodes are outliers and they're famous Nobel Prize winners, basically, physicists, which means the algorithm does. So you don't want to think outliers are always terrorists, right? They can be outliers in excellence. So that's an example. So any questions so far before I move on? So the first time I said, how do I visualize a network, right? Second is, if I see a network, can I identify abnormal behavior? And remember, this is not only for social networks or co-authorship networks. This is the collaboration network. But it could be for Internet of Things. And yesterday I was working with colleagues about the possibility of identifying anomalies in networks of sensors. Or even today, we talked with Jeff about anomalies of LTE networks and the corresponding radar or social networks that come along in the cognitive radio system paradigm. So let me move now to the next problem I have planned. And this relates to inference from partially observed processes on graphs. So basically, this goes back to, not here. So this goes back to the point where we have huge numbers of data. We cannot look at all of them. And the goal is to pick up some of them that hopefully are representative and impute or infer the rest of them and possibly predict outside the available data windows that we have. Okay. All right, so again, let me start with the undirected graph. And let me give you an example before we go. Suppose that you can think of it as a transportation network, right? So every node is an intersection, for example. Think about smart cities. And then suppose that I'm interested about figuring out the average delay from point A to point B in the city, right? So this is the average delay. You go through different paths, right? You're in a big city. Here in Blacksburg, you may be able to count each and every one. And there are many points, but still. If you start including the entire Virginia, right? That includes DC and beyond. Then you cannot afford at any given point to measure all the delays. And by the time you measure them all, the pattern, traffic pattern has changed anyway. So you sample some of them. And you want to figure out what is the delay on two paths that you have not sampled. You come up and say, well, how can I do that? I measured, say in Blacksburg, 4 things. How can I know for every point to every other point what is the time it takes for me to drive there, right? Well, think about the following fact. Price fork is a script that price fork, right? Yeah. Okay, good. So that's what I realized, that if traffic, shows up in Blacksburg, if price fork is congested, Perry and is also congested, right? It makes sense, right? If many routes involve the downtown of any city, right? So if I get information from 2 of them that cross, there's a huge chance that another route that uses this downtown area will also be congested, right? So this is the correlation we're trying to exploit to figure out whatever we cannot observe. Okay, here's the mathematics how we can proceed. Suppose that we measure the delay on node n, this is intersection in my example, at time point t, 5 o'clock, for example. So we measure a subset of nodes because we cannot afford. Remember at the very beginning I told you we have massive data sets. So this matrix M could be a matrix of zeros and ones that will be formed by rows of the identity matrix, and therefore they select a few measurements from X. Is that clear? So this is a selection matrix, 0, 1 entries. So my objective, as I said, is if someone gives me Y, which is a subset, can I find the ones that I did measure? That's number one question. And number two, if I know 5 o'clock, can I predict 5:30? What's going to happen at 5:30? So these are two goals. Well, I mentioned this. Let me talk about the approach we took to this problem. We relied on low-rank matrix completion problems that involve dictionary learning, that take advantage of the dictionary learning model, because the existing approaches cannot predict. They can impute, but not predict. So in our case, we adopt and learn a basis of expansion coefficients. So we say that every vector xt that represents my all the any-to-any path delay is expressible by a basis of it that is described by a dictionary V and a matrix S that is generally sparse. Why? Because I'm not using too many blocks to go home, right, from the measurements. That's the sparsity. And also, every path delay is the superposition of edge delays, right? And there are a few edges that I'm following. So I'm getting through a few intersections. That's what I'm saying. So we formulate this optimization problem to solve over the coefficients S of the basis expansion, the basis vectors, which we normalize to 1 for uniqueness purposes, and then we use again the least squares cost and impose sparsity on the representation, parsimony in other words, which is prevalent in nature. And we're going to use the smoothness over the graph. And it is the smoothness over the graph that enables the extrapolation or the prediction. And it's the smoothness over the graph that allows me to say that if I know the delays in a few paths, I can figure out the delays of paths that look similar to it. All right. So this is possible because the Laplacian of a graph, which is formed by the adjacency matrix, remember I told you at the very beginning what is the adjacency matrix? It describes the topology and the connectivity of nodes with zeros and ones, right? If node I is connected with node j, you have 1. So the Laplacian of a matrix is formed by the adjacency matrix and a diagonal that sums all the rows of the adjacency matrix on the diagonal. So it so happens that this quadratic term that you see here boils down to this quadratic form where Aij is the Aij entry, so it is non-zero if these two are connected. And this quadratic term at time t tells you how far the node I measure is different from the node j measure. So if you minimize this, you enforce smoothness of the process that you're observing over the graph. Okay, so we are solving this optimization problem, and here is how the algorithm works. It goes in two phases. In the first phase, we start from the data we have, which is limited, and we use this optimization function to solve alternately over the basis, K is the interaction index here, over the basis or the representation coefficients S. So we freeze a basis, for example, it could be Fourier or Legendre or whatever, and then we find that using sparsity, the representation coefficients of the basis. And then once we have the representation of the basis, we can go back and solve for the basis B. Let me illustrate that this can be done in this function. If you know S, then you are linear with respect to B, roughly. And because you have this quadratic term, it boils down to ridge regression, basically. So it's again closed form. And if you know B, then it's a lasso problem, which, because you have the normalization over S is a lasso problem, and therefore, alternatingly, you can solve it in closed form in every iteration. So once the training phase finished with the Y, right, you have the measurements, then you can extrapolate. And once you freeze the basis, you can always predict S. And once you predict S, you can go and find X. So you can even find places where you don't know. The proof of the pudding is in the eating. So let's look at the real data from Internet 2. This is link count measurements. So basically, you are sitting at every link of a network, and you find how many packets pass per unit time. And you do that for some, and then you infer for the rest. Or you can, as I said, you can look at the end-to-end delay of some paths and figure out paths that you have not measured as well. So these are, so that you measure things, you call them Y, and you're going to find everywhere you call them X, right? So this is the backbone network of the entire universe. This is the real data. I don't remember which date. But here is the training phase. This is the predicted link load, and this is the actual link load. So you see that we are exactly at the diagonal, that means we do a very good job because we have skipped some of them to test them. And then in the operational phase, we are having 30 links predicted, and except for the low loads that were eventually going up to the, so the actual node is the ones that we're predicting. So we're doing an excellent job with this optimization problem. You can even, so the bottom line is that prediction improves as the link load increases, of course. So just to have a quantitative measure, we define the normalized prediction error. So we set aside some measurements that we pretend that we don't know, and we try to predict them. And that's the mixed-square prediction error over the ones that we are getting that we have set aside. So these are the competing alternatives from AT&T. This is a gravity-based and some diffusion wavelets by Koifman. So this is the average normalized prediction error versus the number we use to predict how many links, how many paths we use, 30 to 50. And let's see, there's an order of magnitude inaccuracy. This is 10 to the minus 1. This is our case, basically, with 30 links. And if we have 50 links, we can even do better. But in both cases, we do much better than what the industry is using for the same problem. This is monitoring the health of the network, right? So how the delay propagates over the network. And you can imagine that once you have a depiction of this, then you can go back and implement, alternative routing methods and so on and so forth. So let me go to the last topic of, I guess I will have time to touch upon. And that has to do with topology derived from information cascades. So let me motivate the subject. We're witnessing on a daily basis with the new president, especially, a lot of popular news stories. And let's go, for example, the alternative facts as a contagion, right? I don't know if you heard about it. I have to be careful where I say what I say, but anyways, we can also think of infectious diseases and how those propagate through the population. So these are time-varying networks that I want to follow through cascades. And just for something that all of us are familiar with through our ordering of products over Amazon, then you can have different products and try to monitor buying patterns of different clusters of users, students, and professionals, and so on. So what is clear is that all these stories, or infectious diseases, or buying patterns propagate through networks. And these networks, sometimes they are explicit, but in many cases are implicit, all right? So we don't basically observe. So the topologies are observable. Sometimes I don't know who is connected with who in the habits of buying musical instruments, because I don't know who is connected with who. So these are observable, and they change with time. Tomorrow, the president may talk about Mexico or whatever. So what's the goal at a high level? The goal is to track an observable and time-varying network topologies from cascade traces. All right? So the first question is, can you quantify this word, cascade traces? And let me try to do that with a picture again. So suppose we look at different snapshots, time 1, 2, and 3 of the same network. And let's talk about, infectious diseases. So at the beginning, you have node 1 that is infected, and these 2, 3, 4 are connected in a certain way. So in the next time slot, we see that different nodes are infected or receive the news, and the connections may change. Some connections may emerge, such as the connection between 1 and 4, and 6 and 7 that were not present. And sometimes they may disappear, some of them may disappear as well at time point 3. This is, the red shows how the news spread or how diseases spread and who's connected with who. For example, if you talk about drug addicts that share needles and are friends or go to same houses and things of that nature. These are the links you can think of. So, what are the measurable quantities? The measurable quantity for sure is the infection time of a node by a cascade. So, for example, what time a news item appeared on a blog? That's the time. Infection time. Also, how susceptible is the node to infection? So if you are into politics, you are more susceptible than someone who cares about, hockey, football, or something, right? So these are the two things that can be measured. And our work postulates that basically cascade infection times depend on causal interactions among nodes. So these are what we refer to as endogenous variables. So within the network, within the graph. So if someone is connected with somebody else, and both of them support a certain football team, then it's likely that they pass on news to each other. And as I said, the susceptibility is something exogenous influence of each node. And both of them are extremely important for identifiability purposes and also directionality. And directionality pertains to the point of which node influences which node. Is me influencing Luke, or Luke influencing me when we talk about benchmarks of academic departments? So directionality is also important. So here is how, out of this abstract, generic, high-level description, we formulate our problems. So we said, okay, let's assign variables to things that I talked about. So YICT will denote the time that contagion C showed up or infected node I at time slot T. Okay? So this is YICT. And we postulate that the left-hand side, so wherever the node I was infected, is a linear combination of all its neighbors, the ones that he or she is connected to, and whether these people were infected by this piece of news or buying pattern or whatever. These are the endogenous influences, the first sum. Is that clear? So we look at which node J is node I connected to. And then we have another term, which is BIIC, XICT, XIC, which is the exogenous influence. And we assume that this does not change over time. And this is your susceptibility to any type of cascade we alluded to. This is exogenous to node I. And we have n nodes. This equation is called for all n nodes and for all C contagions and for all T time horizon slots that were considered. That's a linear equation, basically. Okay. So the topology is captured in what variables? The topology which is observable is captured in the variables Aij. Why? If Aij is 0, then I and J are not connected. Right? Is that clear? So if I manage, by solving this innocent-looking system of linear equations, if I manage to find Aij, I know the implicit network. Right? That's why these models that showed up in psychometrics and social sciences first are called structural equation models. We did, our major contribution is to bring it to network science and also attach dynamics to it. But people back in the 70s even have followed structural equation models that describe the structure of what they're trying to do. And needless to say, I picked up the simplest possible. You can be as sophisticated and non-linear as you wish. But the linear model in many cases is pretty good. So suppose now you collect all these y's into a matrix YT. You collect it over all i's and over all c's, right? So you build the matrix YT, and then the adjacency matrix AT and IT and X are the exogenous variables we talked about already. So you can imagine now you have a system of linear equations. You are given y's and you are given x's, and you are trying to find A and B. That's as simple as that. So given a cascade, the problem statement now concretely stated, given cascade data YT and X, you want to track the topology AT and the external influences BT. Is that clear? Okay, so the next question is, okay, how do network topologies evolve? And we still work on different dynamic models, but the first two approaches we took was the slow varying topology, which would be something that Facebook friendships and web page links change slowly from day to day. Like you don't get all of a sudden 200 friends. But sometimes there are abruptly switching topologies. So if you are, in November and you are into politics, after a major debate, you see a lot of polarized blue and white clusters of people. In ordinary times, they are blended, right? And if you have Super Bowl time, things a sports event may change all of a sudden, the connections. Okay? So let's talk a little bit about slowly varying topologies, and people that are familiar in signal processing with adaptive is really around. Yeah, adaptive signal processing would relate perfectly to that. So in adaptive signal processing, you add what is known as a forgetting factor, and you solve the least squares problem, like the one I formulated earlier. And since we know that the connections cannot be as many, or in a network you are not connected to everyone, then it's reasonable to enforce a sparsity constraint to make your life easier. And also the 0, 0, the diagonal entry of the adjacency, since you have brought the yi on the left, it got to be 0 on the right, and it's only separate independent influence matrices B. So the edge sparsity is encouraged by the Graph-regularization, and the dynamics are tracked through the forgetting factor beta, which is typically chosen to be less than 1. So we have a optimization approach. I don't want to go into the details. It relies on proximal splitting methods. But for me, it is fun to show you the real data that we have. So we went after the infamous North Korean leader, Kim Jong-un, how he came to power. So basically, you look at 360 websites and 466 cascades. So you look at whenever this Kim Jong-un man was mentioned, and the time it was mentioned, and 10 weeks before he came to power, things looked this way, and all of a sudden his name and the number of edges increased, and the density after he started killing, number of relatives. And this corresponds one by one to different needs of a curve here. Here I'm showing the total number of edges in the same network. So you see that not many people were mentioning the name, and all of a sudden, when you monitor the events, you can associate. This is the point where he appointed as vice chairman of the military commission, and then he started killing someone. The death of, I think he said, was uncle, and then he became the ruler in the 40th week, where everybody was mentioning the same thing. So these are the things we have done. I wanted to mention something else, namely abruptly switching topologies, but running out of time. So it amounts to basically simultaneous clustering and estimation. So you basically identify to which state your adjacency method belongs to which cluster it belongs to, and then you solve the problem as before. And we have again real data on web mentions of popular memes like Fukushima and Osama and Steve Jobs. It was the time that he died in the Arab Spring, and then you can identify how the network changes, or the use network changes depending on who is done what. All right, so another, just to flash one more thing that a lot of people are interested about, identifying communities in large-scale networks. That would correspond to, it's like a clustering problem over graphs. So it's like a graph partition type of problem. And the challenge there that we addressed, and I will just say a word on it, is to devise random drawing algorithms of nodes and be able, from a subset of nodes that we have drawn, to identify cluster heads and solve the clustering problem over graphs with billions of nodes. So this is exactly the main challenge of this big data era that people talk about, right? You oftentimes think of solving a system of linear equations, which is maybe 100 by 100 or million by a million. So oftentimes the unknowns are not that many, there in the hundreds, but the moment I tell you you have a billion equations, right, then you understand what big data means, and then you also understand that being able to decipher informative entries of data from huge amounts of data becomes really, really challenging and interesting in a number of fields. And that's the holy grail of one of the, why big data is major area. Okay, I'll close by touching upon what this talk was planned for.
is to develop network science analytic tools under the umbrella and the toolbox of signal processing, machine learning, optimization, and networking. So I touched upon network visualization under hierarchy and scalability constraints. So if you want to basically systematically plot networks where you respect the importance of different nodes to stand out, and it's like a dimensionality reduction over networks, right? Then I talked about how to do monitoring for anomalies and help and do prediction over or inference over networks with known topology. So both of the first two, the topology was known, and it helped me to carry out either the visualization or the prediction or the anomaly. No, the second one, the anomaly did not have that, but the prediction used the topology, the Laplacian of the graph. But the other two switch gears to a problem where the topology is not known and it's implicit. How can you decipher the topology of a network when you don't know the edges? And I just touched upon social networks mainly with my real data experiments today. But I want to talk to you about another, just say a word, fascinating area of research for topology identification are brain networks. So what part of your brain is connected to what part of your brain? The only thing sometimes that you can measure from fMRI are basically nodal processes, concentration of blood or in different regions, and things of that nature. You can figure out things that happen in your brain. So I talked about tracking dynamic network topologies and just alluding to the possibility of using randomized techniques for unveiling communities over large graphs. So what do we do these days? We look at multi-kernel approaches for nonlinear or causal dependencies. Remember, I postulated that, for example, the structural equation model is linear. So the time I was infected or induced at my node depends on what my neighbors did or my connections. But who knows that this is linear? Who tells you that this is linear? And you apply nonlinear approaches and multi-kernel approaches that help you land on linearity. Tensors is a very natural tool if you want to go to multiple dimensions, not only matrices that I touched upon. And of course, if you look at big data, then computing issues become really important. How to make them scalable and parallelizable to implement them on big data computing platforms is also a challenge. And on that, I want to thank you for your attention and open